Hello, my name is Jay Kremke. I'm the product manager for SUSE High Performance Computing. I'm going to take you through a number of topics around SUSE's high performance computing roadmap. If we look at our agenda, I'm going to tell you about why we're interested in HPC, why SUSE has been very popular with HPC for a number of years, and why we see an expansion coming soon. We'll talk about some of the customer challenges in HPC environments. I'll talk about what SUSE brings to HPC beyond just an operating system, and a little bit about where we're going in the future. So first, why HPC? Well, number one, worldwide HPC revenue continues to grow. In fact, as you'll see in a later slide, we're thinking it's around a $44 billion business in just a few years. So it's something that's been around a long time, and it continues to grow. Systems are being built today that are leagues beyond anything that we could do just a few years ago. And of course, everyone is going for an exascale type size computer. So very, very large computers. HPC market is growing. And at the same time, we're seeing more people actually using HPC. So it's not just the traditional modeling, simulation, genomics, those kind of applications, but we're also seeing HPC being used in finance and in retail and a number of other areas. Now, SUSE has a long history in high-performance computing. In fact, 21 of the top 50 supercomputers in the world are running SUSE today, or SUSE-derived operating systems. And that continues to the overall top 500, where we have, in the top 500 rather, where we have 53% of the overall market share, which is much larger than anything else that's out there. So while you might think that supercomputers will run free Linux, in many cases they do run commercial operating systems, and in that environment, SUSE-derived operating systems are definitely the leader. Now, cloud computing is something that's been growing fairly rapidly for several numbers of years, and we're seeing an increase not only in the amount, but also the spend there. And this is the number I talked about earlier. So the people at Hyperion are seeing that the total HPC spending, cloud and on-prem, is expected to be about $44 billion in 2022. So that's not very far away. And most HPC sites today are already running some jobs in public clouds. Public clouds, of course, have a lot of benefits. They don't require large capital investment. They allow people just to kind of pay as they go. And so it's very, very attractive for a lot of customers, either in their prototyping stage where they're trying to define, how big the problem is and what they'll need to do it on-prem, or in a combination of on-prem and hybrid. And then, of course, there's some people that are totally in the cloud. So we see public clouds continuing to grow. Now, it's important that public clouds are not appropriate for all particular workloads. You really need to look at the amount of data that you're dealing with, because moving data in and out of public clouds tends to be fairly expensive. But overall, we're seeing a pretty tremendous increase in cloud use, both private and hybrid clouds. Now, in an HPC environment, if you think about an environment that may have, tens of thousands of compute nodes in there, along with thousands of very long-running parallel jobs, it's a really complex environment. And so a lot of people really struggle with, how do I get up and running as quickly as possible? When you get a large HPC system in-house, there's a lot of work that you need to do, not only in the physical infrastructure, but setting up the parallel software needed to run most major applications. And I'll throw in the added challenge that the parallel software commonly used in HPC environments, particularly the open source parallel software, which is predominant, is evolving all the time. So not only is it large and complex, but it's actually changing all the time. It gets to be really, really difficult to do. And in fact, most HPC environments are kind of do their own thing. So each one might have very unique environments. And later on, when I talk about the Catalyst UK project, I'll point out some of those differences. Now, once you've got the system, kind of built and put together, you do have to maintain the thing, right? You have to worry about patch management, particularly government HPC environments have to put patches on very, very often. They can't let their systems run with exposed security exposures. So that's something that has to be managed. You have to build that in. How do you do that? Do you update the individual nodes? Do you roll out new images? Lots of complexity there. And of course, as I said before, lots of different components that are provided by multiple different vendors makes it really, really challenging. And all of this is because this is, in effect, a very complex environment. I'm going to talk a little bit about LRZ in a moment, but their environment has about 4,000 compute nodes in it and a number of service nodes associated with that. And that's sitting on top of a complex parallel file system and a very high-speed interconnected network. So lots and lots of complexity in these environments. And so we're looking at how can SUSE help customers manage that complexity, get up and running quickly, and maintain the environment once they've got it up. Now, SUSE Linux Enterprise High Performance Computing is now a separate product. It has been for a couple of years now. It's a bundle of the operating system, but also a number of different HPC utilities and something that we call the HPC module. We'll talk more about that in a moment. Now, today we support actually two architectures for high performance computing: the traditional x86-64, both Intel and AMD, and ARM platforms. And ARM is a really interesting platform. It's emerging. There are not very many systems today that are capable of running HPC workloads, but they are also unfettered by the legacy that is tied to x86. So that gives them a lot more flexibility to do things like increasing memory channel bandwidth or I/O bandwidth that is simply very difficult to do with a legacy environment like x86-64. Now, there's a broad range of ISVs and partners and IHVs involved in high-performance computing. I'll highlight some of the ones that we work with a little bit later on. And one of the challenges with high-performance computing environments is once you get those set up, once I get those 4,000 nodes set up, now I have to worry about servicing it. And, you know, with a normal SUSE service life for a service pack of about 18 months or so, they need to look at other options. And SUSE does provide some additional options for elongating the service life, specifically for high-performance computing. And then one other thing we always have to keep in mind with high-performance computing is that these large environments are largely driven by price as one of their primary characteristics. And so we need to make sure that our pricing for SUSE Linux on HPC is competitive. And we went through a pretty extensive exercise several years ago to fine-tune our environment and our pricing. And the two things that kind of came out of that is, number one, we have a much simpler pricing model than our competitors. And number two, we think that we're quite aggressive on price. And in fact, if you look at HPC pricing compared to a normal general purpose operating system, you're talking about something around 75% less for HPC than for a commercial, commercial general purpose environment. So we do have aggressive pricing there. The idea is to allow customers and our partners to be able to get exactly what they need without having to worry about doing special bids and things like that. Now, I mentioned LRZ, or the Leibniz Supercomputing Center in Munich, and I actually had the privilege of visiting them just a month ago before all this stuff started today. They have a very large system that is used for earthquake simulation. So effectively what they're trying to do is improve the ability to simulate what an earthquake will do when it happens, and also to do some predictions, to be able to tell how when those things are going to be coming around. And the calculations are really, really complex. So I think LRZ started out with about 3,000 units. I think they're over 4,000 today. So it's something they continue to have to grow simply because the problems are really, really tough. So think about, thinking about an environment that's got 4,000 computers running the fastest Intel chips that are out there, tied to an InfiniBand interconnected network running on with parallel storage. So a really complex environment, really big environment. Now I want to talk about some of the things that SUSE does around high-performance computing. And of course, the foundation is really SUSE Linux for HPC and the HPC module. And we'll talk more about these in a moment, but this is really kind of our base foundation of providing the operating system and a number of different utilities specifically for HPC. And as I mentioned a moment earlier, this is a separate product from SUSE Linux Enterprise Server now. So that gives us some additional flexibility to do some things in the future that we wouldn't have been able to do if we were still part of SLES. Now, I mentioned HPC in the cloud. We have initiatives and actually images out there for both Azure and AWS, and there's others in the works. So HPC in the cloud is definitely part of our business today. It is a rapidly growing business, a very small base at this point, but we expect to see this continue in the future. And I have talked to customers that are using both on-prem and either Azure or AWS, or they actually can switch between them depending on their particular needs. So HPC in the cloud is definitely going to be even stronger in the future. Now, I mentioned earlier about ARM and some of the reasons why ARM provides some kind of interesting capabilities. So if you look at a traditional x86 environment, basically there's, two vendors. There's AMD and Intel primarily, and that's pretty much it. And they produce a number of systems that the normal ISVs like HPE, Dell, Lenovo, etc. Actually bring to the market. In the ARM environment, by contrast, there are literally thousands of providers of ARM chips. So ARM, the company, licenses their technology that is then picked up by people like Marvell and others to actually produce their own systems. And that gives a lot of flexibility, a lot of new capabilities that are very, very, very interesting for high-performance computing environments. And we're only at the very beginning of this. Now, I mentioned storage a bit earlier. Just about every high-performance computing system deals with petabytes and petabytes of storage. I saw one radio telescope application that I think was generating 30 petabytes a day. So storage is a real big problem for our customers in high-performance computing. Both how do they manage the parallel file systems that are there, things like Lustre, for example, and then what do they do with the data once it isn't needed immediately for computations? They need to put it somewhere. And SUSE Enterprise Storage can actually play a role in both of those, and we'll talk about that more later. Finally, accelerators are extremely important today. So starting about 5 years or so ago, everybody pretty much ran things on CPUs. And, other than some variations that you saw from Intel providing lots of weak cores in environments, we were really CPU bound. But with the introduction of accelerators, such as GPUs from NVIDIA or AMD or other types of acceleration technology, that's rapidly growing. And so pretty much every HPC environment has some amount, if not a lot, of what we call hybrid computing, where they actually have processors, CPUs, traditional processors, plus they're using GPUs or FPGAs or other accelerators. And that provides a lot of complexity around coding, managing, and understanding, what you have out there and monitoring it. So those are all areas that we're working in. Now, containers has really jumped up in I guess about the past 3 or 4 years as well. Traditionally, HPC applications tend to run bare metal because they want to get the absolute most out of their hardware. And while there is obviously virtual machines being used in cloud environments, most on-prem still use bare metal pretty exclusively for their compute. But there's a lot of disadvantages or a lot of challenges with running bare metal. And one of that is all of that flexibility that I mentioned earlier, how the software stack is changing. So for example, you could have one researcher that's using one particular MPI, message passing interface stack, to run their application, while their colleague just down the hall is using a completely different set of MPI libraries and standards. And so one of the challenges for HPC is how do you replicate this, 5 years later when somebody needs to run this? If you were just depending upon what was installed in the operating system, it makes it very difficult to recreate the environment. So containers provide a way of encapsulating workloads so that they can be reproduced later. And you're seeing a lot of work. We'll talk more about this in a moment. And then finally, SUSE can't provide, support for every piece of software that's out there. There's a number of software that, is changing too rapidly, or maybe it's, it's still a bit early. And so we use Package Hub for that. So Package Hub, if you're not familiar with it, is basically a repository of software that SUSE curates and packages and provides it to our customers. And what this allows customers to do is, number one, they can install those packages using the same zipper commands or YAST commands as they would use for any SUSE package. So you got that kind of ease of use there. But what's really kind of useful about it is it allows us to put software out there that maybe is evolving very rapidly, as I said, and it's just, you can't just kind of put a stake in it and say, I'm going to support this software for the next 13 years. So AI and ML frameworks like TensorFlow, for example, are being used out there, and we have that in Package Hub today. And there's also a container technology called Singularity that was specifically designed for high-performance computing and is now available also through Package Hub. And when I say that we curate it, that means we don't just repackage it and put it out there. We actually do security reviews on it. And in fact, as part of those security reviews, we've found problems with some of the open source packages that we've contributed fixes back to the community that the originators of those packages have accepted. So it's more than just simply providing a repository for people to get stuff. Now let's talk about why SUSE Linux for high performance computing. So first off, it's an enterprise Linux with enterprise support. And sometimes when things are all going really fine, people don't think about this too much. But when you have a really ugly problem out there, as we did with some of the vulnerabilities that were in the chips, you really needed to have somebody like SUSE to come in there and provide mitigation for things like Spectre and Meltdown. And so that's important. So in fact, a lot of government agencies and certainly commercial companies all need support at some point, and actually usually have a requirement that they are able to get support. But as I mentioned, we're providing more than just the operating system. And so we'll talk more about the HPC module in a moment with things like Slurm and OpenMPI, but we're also providing deployment templates for head nodes, compute nodes, and development nodes. And I'll show you a bit more about that when we talk about the kind of reference platform. We've talked about aggressively priced subscriptions. So just for example, the list price for an HPC 2-socket system today is $100 US. So that's the list price. Obviously, the prices that customers would pay would be significantly discounted over that. And once again, we do have a track history here. We've been contributing to HPC and been involved in HPC for decades now. And in fact, we're at the core of popular environments like Cray Linux environment is based on SUSE Linux. So there is a lot of SUSE Linux out there running today in high-performance computing environments. Now let's talk a little more about the HPC module. So the concept was, hey, let's find some of these packages that people are often using in a high-performance computing environment. Let's take those in, make them part of SUSE, make them part of a supported part of our product, and provide them as part of SUSE Linux HPC. You'll see a number of ones there. Some of them are libraries, things like OpenMPI or OpenBLAS. Some of them are file system aids, so things like HDF, for example. Some of them are algorithms, and then one of the biggest and most popular ones is a workload scheduler called Slurm. And SUSE has actually been supporting Slurm now, I believe, for about 3 years. And so we actually do provide full support for Slurm. We work with the community to resolve issues and contribute our fixes back to it. By the way, SUSE Linux HPC is available in SLE HPC 12 and SLE HPC 15, though if you're going to do something new, I strongly suggest you go with SLE HPC 15. We're getting the newer kernels there as well as new hardware enablement, and it's really, really where you should be going to. Now let's kind of look at very briefly at a reference architecture. So here we have compute nodes, and then we have some service nodes, things that are called, for example, head nodes or login nodes. Those are things that are used to stage the jobs and debug problems and manage the environment. The bulk of the work is done by the thousands, potentially, of compute nodes that are out there. Now, I mentioned earlier, we have a lot of partnerships around high-performance computing, everything from HPE and Lenovo and Dell to the hardware vendors as well as the software vendors. So a pretty broad range of partners out there. And speaking of partnership, one of the areas that we had an extremely important partnership was this Catalyst UK program, where we worked with the University of Bristol, University of Leicester, and University of Edinburgh. We installed systems, HPC systems, ARM HPC systems in each one of those, and we've been experimenting with understanding, where are there gaps in the software stack, where can we do better, where are there problems that we need to resolve. And as you can see there, we actually were awarded the best HPC collaboration at Supercomputing 2019 last year. So this has been a very good experience, and it's continuing. But like I said, this is the very start of ARM in the HPC environments. Now, talk very briefly about cloud ready. So I already kind of gave you the ideas about how important cloud is to HPC. And so give you a couple of examples here. One example is an all-in on the cloud where everything exists in the cloud environment. We certainly do have customers doing that. All the head nodes, compute nodes, and storage nodes are in there. There's no hardware infrastructure for you to manage. The downside, of course, is that you're paying to use someone else's hardware, and they're not doing that for free. So a cloud environment, while it can reduce your capital expenditures, can result in some pretty stringent, pretty large operating environments. So you need to be able to figure out how to manage that. It's actually quite popular today to see kind of established environments that are using this hybrid model, where they have some amount of hardware on site, and then when the requirements of the jobs are greater than what they have in-house, they can use the cloud to kind of overflow to those. And I know of a customer right now, a German manufacturer that has about 100 physical nodes, and then they burst to the cloud whenever they run outside of that. It's really, once again, tied to how much data do you have to move back and forth to the cloud as to whether this is a feasible choice for you. Now, AI and ML is a very large topic, and my colleague Alessandro Festa is covering that in a lot more detail. But just to give you an example of some of the spectrum of AI solutions, it goes everything from artificial intelligence and then gets, over time, even more kind of convoluted and complex. And so this is an area where we have started to deliver some packages into Package Hub as a way for customers to kind of jumpstart this process. But this is something that almost every HPC customer is using. Some are using AI and machine learning in particular to examine what happens after their runs happen, and then others are actually using it to kind of look at the data that's coming out while it's actually happening to determine if they need to continue running another 30 days or something like that. So AI and ML and HPC are very, very tightly interwoven, and we'll see that continue to increase, particularly as these hybrid environments with GPUs and things like that come in. Speaking of which, I mentioned earlier that with the accelerators that are out there, there's a real challenge for programming those environments. Because if I program something specifically for say an NVIDIA GPU, I can't necessarily pick that up and take it over and run it on a GPU from another vendor, like from AMD, for example. And even in environments where you're staying on the same environment, like FPGAs, it can be a real challenge even moving to a different model FPGA within the same product. So having some level of an abstraction level is one of the things that we're supporting with our participation in OpenACC. So this is something that we're doing in partnership with NVIDIA and a number of others, but it really is to help simplify programming access to accelerator technology. Now, I mentioned Package Hub multiple times now. It is something that we provide to our customers as a no-cost benefit. It's community-supported software, and it is installed via the normal tools, Zipper and Yast, for example, and we do curate these packages. And a few over there on the right that you see that are important for this discussion, TensorFlow, Caffe2, Theano, NumPy, PyTorch, those are all AI and ML type packages that are associated with high-performance computing, and those are now available in there. Well, PyTorch is coming soon. And then you see some other things like Cluster Shell, for example, which is and Robinhood, which are utilities that can be used to help manage an HPC environment. And then the final one there on the list is Singularity. So Singularity, as I mentioned earlier, is a container alternative to Docker containers and some of the other container types that are out there. It was invented specifically for high-performance computing, and we make that available to our customers through Package Hub. Now, everything in Package Hub is community supported, but behind every package that's out there is usually some SUSE people that actually understand that package and that utility very, very well. Now, I mentioned SUSE Enterprise Storage, and for many, many customers, managing storage is a real challenge. And so having a software-defined storage approach, a software-defined storage approach where you can actually, add on capacity as you need it without having to, continually buy new hardware all the time. Sorry for that. We have a slide for it. So SUSE Enterprise Storage, been available for some time now. It's got a very, very easy to manage interface in it, and we've actually been working with it with the IO500 benchmark. And in fact, SUSE Enterprise Storage actually had a benchmark in some that was actually faster than Lustre Parallel File System in some cases. And I'm sorry, I've got some slide advances in here. Now, University of Maine is one of these customers that's using SUSE Enterprise Storage as a primary file system, but there are others out there. This is an example of showing how you can use SUSE Enterprise Storage as Tier 2 storage. So in other words, after your computations are done, let me move the data off the low latency parallel storage to someplace else so I can keep it near line. And then when I need to run that job again, I can use technology like the HP DMF7 to actually bring that data back in, completely transparency to the end user. So this is an example where we're able to kind of maximize the use of the parallel file system, things like Lustre, for example, and then transparent to the user, actually bring this workload, bring that data back in when we need to run another job. And I've got a slightly different example of that with a large European energy company that has a large HPC and AI compute cluster. And once again, they have high performance storage, that's Lustre, it's 10 petabytes. And then behind that, they have SUSE as kind of their Tier 1 storage. So the place that that stuff can go when it's not being immediately used in computations. And so once again, this is an example where customers using DMF to be able to have that data recalled automatically to their parallel file system. And so it really simplifies the management of this. Now, if we look overall at the life cycle for SUSE Linux HPC, you'll see that it's quite similar to what we have for SLES. So in other words, about every year, you get an update to the underlying version with a new service pack. And so in the case of SLES 12, we've released now what we think is the final service pack, and that was SLES 12. Service Pack 5 came out at the end of 2019. And you'll see in the blue there that there's the normal about 18 months of support life for any given service pack. And so the way that SUSE normally works is if you're on a service pack, let's say that you're on service pack 1 there down for SLES 15 or SLE 15. When service pack 2 comes out, you have about 6 months to transition to the new service pack before you are not able to get service anymore. So we added 2 things to kind of extend the service life for HPC. So the first is something called SPOS, and this is a concept we borrowed from the SAP guys, and that stands for Extended Service Pack Overlap Support. So you see that slightly brighter green there next to the blue bars that says SPOS. So this effectively gives the customers 1 additional year of support on a particular service pack, so they don't have to worry about upgrading if they have a problem or anything like that. They can stay on that for, basically for 18 months plus a year. And we actually bundle this in a special SKU where the customer can buy this. And I mentioned earlier that the base SLE HPC subscription is list price of $100. Well, that SPOS only adds another $20 list price on top of that. So for $120 list price, you can have a much longer service pack life cycle for your high-performance computing environments. Now, if you need more than that, or if you didn't purchase the SPOS and now you find yourself needing support after the normal 18 months, then we do offer long-term subscription support, LTSS, but we offer one specifically for HPC. And so like SLE HPC, it's offered at a significant discount compared to what we would charge for LTSS for general purpose SLEs. And so that gives you then, another up to 3 years of long-term support. So these are some of the ways that we're trying to make it easier for our customers to be able to stay on a given release for a longer period of time. Now, if you look at where we're going in the future, obviously, always enabling and exploiting new hardware is important, and that's something that we have to do just day to day. As Intel and AMD and the various ARM vendors like Marvell or Fujitsu or what have you come out with new hardware, we have to enable that. And that enablement work has to happen usually about 1.5 to 2 years before the hardware actually shows up in somebody's shop. So that's a long-running, long-purpose thing. Now, I showed you some of the HPC module things a while back, and there were some libraries in there and some utilities. We're actually shifting our module to focus more on utilities. And the reason being is that in the case of libraries used in HPC, most of our customers actually prefer to build them themselves. And there are a lot of variations on building those libraries depending upon what high-speed interconnect you use and a number of other factors. And so it's really kind of too presumptuous of us to be able to release libraries out there that we would expect our customers to use. And the other thing is that those libraries are changing all the time. I looked at one of them, MVA PIC. I think it had 4,000 library dependencies on it. So, and all of those are always changing. So focusing on utilities is certainly an important part of this business. Now, blending in AI and ML support is something that is quite important. And although we have plans to actually release AI and ML technologies to our customers directly, they're very important for HPC. So we need to have offerings that combine both the traditional modeling simulation type of things in HPC along with tools for the AI and ML environment. And then one other thing that we're doing at SUSE, not just for HPC, but across many different products, is how do we improve our day one and day two experience? So not all of our customers, have used SUSE in the past. And so we need to make sure that when they go out to install a new HPC cluster, they've got guidance, documentation, tools on how to do that. And then as they're managing it, they also need to have best practices into, how they can do that. So there's a lot of work to be done there. It is a very diverse environment, so we're going to have to figure out which things we think are the best approaches, and we'll probably have, maybe different approaches for different types of workloads. So I know I didn't have a lot of time to go through this, but I want to thank you all for participating in SUSECON Digital, and thank you for watching my presentation on high-performance computing. And I hope to hear from you. My email's right there, jk@suse.com or @Mr. Sless on Twitter. So thank you very much and have a good day.